Hello, this is Differential Equations Exam 3 Review Problems and Solutions. For the most part, we're going to be looking at a lot of examples of linear systems of differential equations in vector and matrix form, finding eigenvalues, finding eigenvectors, finding general solutions, finding unique solutions of initial value problems, making phase portraits, that kind of thing. We'll do a little bit with mass on a spring harmonic oscillator. I'll also talk about the matrix exponential and flows a little bit, and we also have one problem involving Euler's method for two-dimensional systems. So we're starting with kind of an abstract problem, but a pretty fundamental problem. Suppose lambda is a real eigenvalue of a square matrix A, and capital V here is the corresponding real eigenvector. Let capital Y of t, a function of t, equal e to the lambda times t times the vector v, this scalar multiple of the vector v that is a function of t ultimately. Note that this vector is always on the same straight line through the origin because it's always a scalar multiple of a single vector. It's on the line parallel to v. Part A says, show the steps of a calculation that confirms that this function is a solution of this differential equation dy dt equals a times y. Note you'll need to use the assumptions as an extra hint in the first sentence at some point. And part B, there's a special name for this type of solution that I've taught my students, and I'll teach you if you don't know it. All right, so what do we do here? As I always emphasize with differential equations, when you've got a formula for a possible solution, you need to check it in the left-hand side of the differential equation and the right-hand side and see if you get the same thing. So we go ahead and we do that. The left-hand side of the differential equation is dy dt. It is the derivative of this vector-valued function of t, which is really a parametric curve lying in a straight line in this case. We need to differentiate this in the way that should seem pretty obvious. We need to differentiate e to the lambda times t and then still multiply by v. We'll need the chain rule. Lambda is a constant. When we differentiate e to the lambda t, we'll get e to the lambda t times lambda. I'll bring the lambda out in front. This is lambda times e to the lambda t times v. And there's really not much more you can do right there. That is how the left-hand side of the differential equation simplifies when you substitute this function. What about the right-hand side of the differential equation? RHS, that's a times y. The idea is you replace y with the function that you're trying to check is a solution. So replace y with e to the lambda t times v. We got a matrix times a vector. E to the lambda t times v is a vector. It's a scalar times a vector, which is a vector. There's a property of matrix multiplication that allows you to take the scalar and put it out in front. I can take this e to the lambda t, which is a scalar, and put it out in front of the entire thing and write it as e to the lambda t times a times v. Now, what do we need to do? We haven't used the fact that lambda is a real eigenvalue and v is a corresponding real eigenvector. We haven't used that fact yet, okay? And actually the real part only comes into play in interpreting the geometry of the solution as being on a straight line here. How do you use that? You need the fundamental eigenvalue-eigenvector equation. What does it mean for lambda to be an eigenvalue and v to be a corresponding eigenvector? It means a times v is lambda times v. That does not mean a equals lambda, okay? A is a matrix, lambda is a number. But these two vectors are equal, a and lambda are related to each other. Now just use that. I can replace a times v with lambda times v, and then I can pull that scalar out in front and rewrite this as lambda e to the lambda t times v. Lo and behold, that expression equals this expression. Those are equal. We're very happy. That means, yes, we're done. We have confirmed with calculations that this is a solution of the differential equation. What kind of special name does it have? It's hinted at in the fact that it's on a straight line. It's called a straight line solution. It is a straight line solution. If you graph it as a parametric curve in parametric mode on your calculator, for example, it will be on a straight line. It won't be really a curve. It'll be a straight curve. Straight line solution. That's what it's called. And that's very special. That helps you find what are called eigenvector bases for the plane, and that helps you find the general solution, as we will see in some examples. Number 2, we got a particular matrix A here. Entries -10, -8, 16, and 14. Part A says show work to find the eigenvalues of A. And then part B, for the corresponding linear system of differential equations, classify the equilibrium point at the origin as a sink, spiral sink, source, spiral source, or saddle point, okay? So you need to know how the eigenvalues help you classify. I'll talk about that after we find the eigenvalues. How do you find the eigenvalues? You need to compute the characteristic polynomial, which is the determinant of A minus lambda I, and then find its roots. Those will be the eigenvalues. Determinant, this is the matrix A. I'll go ahead and maybe show an extra step here. There's A, -10, -8, 16, and 14. Lambda times I is lambda times the identity matrix. The identity matrix has a 1 in the top left and lower right and zeros elsewhere. 1's on the main diagonal. If I multiply that by the scalar lambda, the number lambda, I get this matrix, lambda 0, 0, lambda. Now go ahead and subtract those matrices, entry by entry. That's how you do matrix subtraction. So you get ultimately the determinant of -10 minus lambda, -8. Down in the lower left, it's going to be a 16, and in the lower right, it's going to be a 14 minus lambda. Go ahead and now take that determinant. It's a 2 by 2, so it's pretty easy. Multiply these two quantities and subtract the product of these two. So I'm going to have -10 minus lambda times 14 minus lambda minus 16 times -8. You got to be really careful with negative signs here. Okay, hopefully I can be careful here too. So we go ahead and FOIL this out. -10 times 14 is going to be -140. Then that's first times first. Outside times outside. -10 times negative lambda is plus 10 lambda. And then we have inside times inside is minus 14 lambda. And then last times last is negative lambda times negative lambda is positive lambda squared. And then we're also subtracting 16 times -8, which is adding 16 times 8. 8 times 8 is 64, so 16 times 8 would be 128. Our characteristic polynomial simplifies to lambda squared minus 4 lambda minus 12. And that is easy to factor, okay? If it wasn't, you could use the quadratic formula, but this one is relatively easy to factor. If you think about it a little bit, you realize it's going to be lambda minus 6 times lambda plus 2. I need those two numbers to multiply together to give me -12 and to add together to give me -4. By the way, there is a shortcut for finding the characteristic polynomial that avoids all this stuff in the 2 by 2 case. This number right there, the 4, is called the trace of the matrix A, sometimes just denoted by a T. It is the sum of the numbers on the main diagonal for A. -10 plus 14 is indeed 4, and that is being subtracted, okay? That minus sign there is supposed to be there. I'm taking lambda squared minus the trace times lambda. This number, including the negative sign, is the determinant of A, sometimes just called D. That's the determinant of A. -10 times 14 minus 16 times -8. That's -140 plus 128. That is -12. You could just, if you know those two facts, you can just jump to this characteristic polynomial without bothering to do all this stuff, okay? You should be able to do it this way, but if I don't ask you to do it that way, you could just jump right to the characteristic polynomial. Anyway, we can factor it, and the fact that we can factor it like this, and then we set it equal to 0 to solve the characteristic equation for the eigenvalues of A. The roots here are going to be obviously 6 and -2. So the eigenvalues that we're after, I'll just call them E values here, are going to be, you could use subscripts if you like. Lambda 1 equals 6 and lambda 2 equals -2. The subscript ordering is arbitrary. I could have said lambda 1 is -2 and lambda 2 equals 6. The important thing is that in this case, 1 is a positive real number and 1 is a negative real number. And that means the origin is a saddle point. at the origin. And the origin is the only equilibrium point here because A has a non-zero determinant. And it is a saddle point when you have one positive real eigenvalue and one negative real eigenvalue. The origin is a saddle point. The reason for that we'll get into as we talk about some examples. I think there might be an example where we have a saddle point. Maybe not. Let me just briefly describe the reason. The general solution, this is not asked for in the problem, but the general solution would take on the form y of t is an arbitrary constant, call it k1, times e to the 6t, where 6 is this first eigenvalue, times the corresponding eigenvector for 6, v1, which I'm not saying what v1 is. I could find it, but I'm not taking the time to do that, plus k2, another arbitrary constant, times e to the negative 2t, use the second eigenvalue, which is negative here, times the corresponding eigenvector for that. And ultimately, what this means is you've got one straight line solution corresponding to the positive eigenvalue where it's exponential growth, and so you have arrows pointing away from the origin, and another straight line solution corresponding to the negative eigenvalue where the arrows point toward the origin, and the other solutions tend to look like this kind of picture here, and that's reminiscent of a saddle point like you would find in multivariable calculus. Sort of if you can imagine the solution curves, for example, running downhill, then if you imagine sort of a saddle like on a horse sitting on top of this, you've got sort of downhill in one direction and uphill in the other direction is the idea there. That's why it's called a saddle point. That was not asked for, just extra information there. All right, on to number 3. Let I be the imaginary unit, and let y of t equal the sum of yre of t plus I times yim of t as a complex valued solution of the linear system. Okay, now you need to know some things here. Linear systems like this can have complex valued solutions, and I'm assuming that in this case. But when I make this kind of assumption, it's implicit, it's assumed that this thing and this thing, in fact, are real valued functions. They are real vectors. These are real vectors here. The imaginary unit comes in there to make this thing overall a complex valued vector. And yes, you can have complex solutions of linear systems. It's less clear how to geometrically interpret them. We will hopefully see that a little bit here. I'll talk about it. I'm saying in my directions, using complete sentences, prove, a little bit of our proof here, that the real valued functions, this one and this one, also solve the linear system. Okay, how do we do that here? Well, think again, just like in the very first problem, of what it means to solve a system, a differential equation. Here it's a system because it's in vector form. It means when you substitute in the left-hand side and the right-hand side, you get the same thing. So we're making the assumption that this is a solution. So we're really making the assumption that when I substitute on both sides, I get the same thing. So we need to use that assumption in some way. How is the question, and how does it lead to our final conclusion? Well, using sentences here, we should say something like this. Since we are assuming, that's the word assuming if you can't quite read it, y of t solves the differential equation dy dt equals ay, we can say that when you substitute, when you differentiate y prime of t, which you do differentiate by doing each piece here individually, that would be yre prime of t plus yim of t prime. Okay, that's a definition of how you differentiate a complex valued vector function, that you're going to get a times y of t for all t. But a times y of t is a times, in parentheses, yre of t plus I times yim of t. And yes, I do like to emphasize this is true for all t. Okay, that's what it means to solve the differential equation. You want this to be true for all t, and that really did happen in number 1. as well. So that is the essence of using the assumption. How did we get to our final conclusion? We're trying to show why RE and why IM are solutions as well. Well, we need to verify they equal each other on the left-hand side and right-hand side when we substitute into the differential equation. It's maybe not super clear how that's going to happen, but maybe you get a little feel for it, and sometimes you just have to do what's natural, what comes next. I hope it feels natural to try to use a distributive property here to distribute the A matrix through the parentheses there. And that certainly can be done. You can say by the distributive property of a matrix times a sum of vectors. And yes, you can use this property. You don't have to prove it from scratch. We can say capital Y prime of t is this, but that's going to be a y RE of t plus a times I times y IM of t, and we can also factor out the I, that's a property. Okay, so I distributed the A through the parentheses there, and that can also again emphasize this is true for all t. Are we done? Well, yeah. This can be plugged in there, and then you can use the true and intuitive fact that two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. The imaginary parts are the things that are next to the I. They don't include the I. Since y prime of t, this is maybe a little overkill here, equals y RE prime of t plus I y IM prime of t, it follows that, and that's true for all t as well, y RE prime of t equals a times y RE of t. The real parts are equal, and the imaginary parts are equal, and I don't have to write the I. Y IM prime of t equals a times y IM of t for all t. And that is what it means to solve the differential equation. And that means I'm done. I can say QED. Maybe you want to add an extra sentence in there saying this means they solved the differential equation. Okay? So you use your assumptions, you use basic properties that you know, and try to get to the conclusion. You got to connect the assumptions with the conclusion. Number 4. This problem, you'll be finding the general solution of this linear system in two different ways. The second of which involves eigenvalues and eigenvectors, but the first of which involves recognizing this is what's called partially decoupled, because the second equation, this one, has no x's in it. So I can really just think about it on its own. I'm looking for a function with the second equation, y is a function of t, whose derivative is always 4 times itself. You can separate variables to solve that, but you really don't need to if you have enough experience. You should recognize e to the 4t has that property. Its derivative is 4 times itself. And any constant times e to the 4t also works. Here I'm calling that constant k2. Well, why am I calling it k2? Because it's in the second equation. k2 is an arbitrary constant. It is the general solution of the second equation. The second equation doesn't involve x. It makes the system partially decoupled because I can think about this one just by itself. And then I can use that fact to figure out the solution of the first one. I can use it to rewrite the first equation by substituting this in place of y. I get this. The 3 here comes from the 3 there. Directions now say, now use either the method of undetermined coefficients or the method of integrating factors, we'll practice integrating factors here, to find a formula for x of t involving 2 arbitrary constants such that this is a general solution of the original system, a vector form of the general solution of the original system. All right, so some directions there to give you some insight into what's going on here. But we just need to take that equation and solve it. I will, again, practice the method of integrating factors. I will first subtract 2x from both sides to write it like this. That is in linear differential operator form is what I call it. It's a non-homogeneous linear differential equation, first order. dx dt plus or minus something times x equals something, a function of t. And the method of integrating factors says that the integrating factors, typically called mu, is e to the integral of whatever's in front of the x here. Sometimes it's a y if it were an equation involving y, but in this case it involves x. So it's e to the integral of -2 dt, which is e to the -2t, plus c. Do I need a plus c? You can take the c to be 0. Why is this called an integrating factor? Well, you end up multiplying it on both sides of the differential equation to get a new equivalent equation. So it's a factor of the new equivalent equation, and the magic of integrating factors is that it makes the equation easier to integrate, easier to solve. So I go ahead and do that. I multiply both sides. I get e to the -2t dx dt minus 2e to the -2t x. Don't forget to multiply it on the right side. That's a common mistake. People forget to multiply it on the right side. Multiply it times this. I'll get 3k2 e to the 4t times e to the -2t will be e to the +2t. Okay? And if you've done it right, this thing right here will always be the derivative with respect to t of the unknown solution function times the integrating factor, or integrating factor times the unknown solution, either way. That will always be the case by the product rule, and you can double check this. There's your first function, there's your second function. This product up here is the derivative, is the second function times the derivative of the first, plus the first function x times the derivative of the second. The derivative of e to the -2t is -2 e to the -2t. Keep in mind x is a function of t here, but I'm not explicitly putting the x of t in there. I am up here. Okay. Now we integrate both sides. This side's easy to integrate. Maybe I should put the integral sign here too. With respect to t, because you're integrating a derivative, you're just going to get this function. So you're going to get, ultimately, x e to the -2t. Integrate this one, you're going to get 3/2 k2 e to the 2t plus an arbitrary integration constant that I think I'll go ahead and call it k1. That's fine. Constant k1 here. It is an arbitrary constant. It doesn't matter what I call it. It'll be fine to call it k1. Not done. I need to solve for x, so I need to now multiply both sides by e to the +2t to cancel it on the left side. So x is going to be 3/2 k2, looking right there. E to the 2t times e to the 2t is e to the 4t. And then plus k1 e to the 2t. And as far as the directions go, I guess we've found the formula for x of t, so we don't really need to write capital boldface y of t as a vector, but I will anyway. This is the answer, but vector y of t would then be this thing in the first component, 3/2 k2 e to the 4t plus k1 e to the 2t, and you could switch those around if you prefer the k1 term first for the first component, and this thing right up at there for the y of t, k2 e to the 4t. Note that there's, this coefficient of 4 and 2 in both of these powers of e. That is related to the fact that we have a 2 and a 4 up there. And that'll come out here in the second part. Second, write down a 2 by 2 matrix A so that this, if y is this vector, then the original system can be written like this. Then find the eigenvalues and eigenvectors and use them to write a general solution. So that's actually using eigenvalues and eigenvectors. Careful about, careful to note which number is in front of which variable. This 4 is in front of a y. It's under the x, so you might get confused and write down the wrong matrix because of that. You might think it's 2, 3, 4, 0, but it's in front of a y, so it's really 2, 3, 0, 4. A is 2, 3, 0, 4, which is an upper triangular matrix. And you could go ahead and find the characteristic polynomial. In fact, I'll write it down using the trace and determinant. The trace is 6, so I get lambda squared minus 6 lambda, and the determinant is 8 plus 8. But if it's upper triangular, the eigenvalues are going to be the numbers on the main diagonal, 2 and 4. This does factor as lambda minus 2 times lambda minus 4. So the eigenvalues, setting that equal to 0 and solving for lambda, are lambda 1 equals 2, lambda 2 equals 4. And again, the subscript labeling is arbitrary. What about the corresponding eigenvectors? Didn't give myself a ton of room here, but let's see. For lambda 1 equals 2, how do you find the corresponding eigenvector? You need to solve a minus lambda times I, which in this case is 2 times I, times an arbitrary vector v equals the 0 vector. That's equivalent to the equation AV equals 2v. Okay, if you think about it, if you subtract 2v from both sides, and then also write 2v as 2 times I times v, and then factor out a v, we're after non-zero solutions of this, non-trivial solutions. They will occur when lambda is an eigenvalue. And if you do that here, what is a minus 2I? Subtract 2 there, you get a 0. Subtract 2 there, you get a 2. It's really 0, 3, 0, 2 times v. Let's label the components of v, x, and y, equals 0, 0. As a system of linear equations, it's really 3y equals 0 and 2y equals 0. It's kind of a strange system. In other words, y must be 0 and x is free. X can be anything. So we're just after one non-zero eigenvector here. The simplest thing to pick would be v1 equals 1, 0. Okay, that would be the simplest thing to pick. X can be anything, and it solves the system. We're after non-zero solutions. The simplest non-zero thing to pick for x would be 1. So I can take v1 to be 1, 0. I could also take it to be 2, 0, or 7, 0, or negative 14, 0, or pi 0. Okay, it doesn't matter as long as it's a non-zero vector. But choosing this one will help it match the other solution a little bit nicer. For the other eigenvector value, and its eigenvector, lambda 2 equals 4, I do a minus 4i times v equals 0, and looking for non-trivial solutions for v. A minus 4i is going to be 2 minus 4 is negative 2, and 4 minus 4 is 0. The second equation, the second line there just says 0 equals 0. We can focus just on the first row of the matrix A minus 4i to get negative 2x plus 3y equals 0. So 3y equals 2x. Let's see, if I want to try to make it match this one, let's see. I should maybe divide both sides by 2 and say x equals 3 halves y. And what I can do is I can think of y as free. You could also think of x as free, but if I think of y as free, then x is 3 halves y, and I could, for example, take y to be 1 and x to be 3 halves. I could also take, to avoid fractions, y to be 2 and x to be 3. Okay, and that would be fine as well, but doing 3 halves and 1 will help us match this one. There are infinitely many ways of writing a general solution. You know, I've got infinitely many choices of v1 and v2 here that I can make. Solutions of initial value problems end up being unique. The k1 and k2, depending on how you write the general solution, could be different things. But when you simplify the final answer for an initial value problem, you'll get the same answer no matter what you do, as long as you don't make a mistake. So, final answer here for general solution I can write as arbitrary constant k1 times e to the 2t, lambda 1, times v1, which is 1, 0, plus k2 e to the 4t, I'll go ahead and use this eigenvector, 3/2, 1. And yeah, if I simplified this, I would get a match. I did write it in such a way that I get a match. Again, not that I had to, but just for the purpose of seeing that I could, I did it that way. Okay? So we got a match. It wasn't asked for in the problem, but sometimes I ask my students to also solve what I call generic initial value problems. For arbitrary vector y sub 0, whose components are little x0 and little y0, can I solve for k1 and k2 in terms of these things, which I'm thinking of as being fixed? Here I'm thinking of k1 and k2 as being arbitrary. It's a general solution, but here I'm thinking of x0 and y0 as fixed numbers. Can I solve for k1 and k2 in terms of those things? And that's a useful thing to be able to do sometimes as well. And the answer is yes. Plug in t equals 0. E to the 0 is 1, so you're going to get k1, 1, 0, plus k2, 3/2, 1, which equals k1 plus 3/2 k2 in the first component and k2 in the second. So that means k2 does have to be the same as y0. And then k1 will be x0 minus 3/2 k2, which is x0 minus 3/2 y0. And then I could plug those things in for k1 and k2 here, and k2 equaling y0, I could plug that in there, and then I get a, if I think of x0 and y0 as fixed, then I'd have a unique solution of an arbitrary or generic initial value problem, and that can be a useful thing. This problem is a linear system that involves drawing a phase portrait in the phase plane. Giving students a little bit of help. I mean, the things I'm telling them in the first sentence here are things they and you should be able to find, but to save time and to save mistakes and to make the grading go easier, I tell them the answer here. The general solution, or a general solution I really should say, of this linear system can be written in this form as a linear combination. Your eigenvectors are linearly independent. They do form a basis for R2, the plane. That's pretty important, actually, for solving the system easily. There are some weird special cases where you don't get two linearly independent eigenvectors, and you have to use some other technique to find general solutions in that case. So evidently the eigenvalues here are -3 and -5. Look at those coefficients of t. And the corresponding eigenvectors are 1, 3 here for -3 and 1, 1 there for -5. Okay, so you could take the time to double check that if you wanted to. Part A is just a quick question. Identify the origin as a sink, source, or saddle point. You've got two real negative eigenvalues. That is going to be a sink. And it's not a spiral sink because they're not complex eigenvalues with, I should say, not complex non-real eigenvalues with negative real part. It's just a plain real sink. There's no spiraling that's going to be going on. So A is a sink. And if you had to give a reason, you'd say because I've got two real negative eigenvalues. B says, find the unique solution of the initial value problem where y of 0 is 4, -2. So that's just a matter of solving a system of equations. 4, -2 equals y of 0. Plug in t equals 0 into the formula. E to the 0 is 1. So I get k1 times 1, 3 plus k2 times 1, 1. I can write this all as one vector if I like. k1 plus k2, and then 3k1 plus k2. It's a linear system of two equations and two unknowns, k1 and k2. You could make an augmented matrix, do row operations if you like, but you don't have to. I mean, it's fairly nice here. You could say subtract the first equation from the second equation. The k2s would cancel. 3k1 minus k1 is just 2k1. I'd have to do the same thing with the constants. -2 minus 4 is -6. So it looks like k1 is -3. And then just plug that back into either one of these and solve for k2. If I plug it into the first one, k2 is going to be subtracting k1 from both sides. 4 minus k1, so that's 4 minus -3 is 7. And you could also double check with the second components here that it works. 3 times 7 3 times negative 3 is negative 9, plus 7 is negative 2. Okay, so the answer for the unique solution, vector y of t, is going to be k1 is negative 3, looking back up here, e to the negative 3t times 1, 3, and then plus k2 is 7 plus 7, looking over here, e to the negative 5t times 1, 1. It's fine to leave the answer like that, but you could also write it as one vector. Simplify the linear combination. The first component is ultimately negative 3 e to the negative 3t plus 7 e to the negative 5t. The second component, negative 3 times 3 is negative 9 e to the negative 3t plus 7 e to the negative 5t again. Okay, there's your unique solution. Now draw the phase plane, okay? We're given some nullclines. Now, if you use the Blanchard-Devaney Hall book like I do with my students, they don't talk about nullclines until chapter 5. This is chapter 3 stuff. But I like talking about nullclines. I think it's a good idea to introduce them early. What are they? They are, in general, curves. In this case, the curves are lines that you see here, where the vector field is either horizontal or vertical. For the x nullcline, it's where dx dt is 0. In other words, dx dt is, think about the first row of this matrix, is negative 6x plus y. There you see negative 6x plus y. Set that equal to 0. Solve for y in terms of x. You get y equals 6x. That's a line through the origin with a slope of 6. That's this line right here. This is not a straight line solution here. It's the x nullcline. Solutions have to cross that with a vertical tangent because the x component of their velocities, so to speak, the velocity vectors are going to be 0. They could cross it going up or down. You have to figure that out later. The y nullcline is where dy dt is 0. Look back up here, and dy dt is negative 3x minus 2y. Negative 3x minus 2y, set it equal to 0. Solve for y as a function of x. You get y is negative 3 halves x. That's this line here. That's where dy dt is 0. The vector field has horizontal vectors on that line. Solution curves have to cross with horizontal tangents. The velocity vectors of solution curves have to be horizontal as they touch that line. Again, it's not clear if they're moving left or rightward. We have to figure that out still. All right, what else can we do? Again, the origin is a sink. We know solutions are going to go toward the origin. We know where the straight line solutions are. This is one straight line solution, and this is one straight line solution, and we're adding an arbitrary linear combination of them. Straight line solutions are parallel to 1, 3, and 1, 1, which it's not going to be the easiest thing to draw here, but we can do it. 1, 1 is a vector parallel to the line y equals x, so one straight line solution is along the line y equals x. It's parallel to the vector 1, 1. And it's for a negative eigenvalue, so your arrows are going toward the origin. I already did make a big dot at the origin. That's the equilibrium point. If it wasn't there, you really should draw it. The other straight line solution is parallel to the vector 1, 3, which is along the line through the origin with a slope of 3. So these lines are kind of close together, which makes it a little harder to draw, but about like that is another straight line solution. Slope of 3 through the origin. Okay? How do you draw in the rest? There's a couple ways you could approach it. One good thing to do is in between the nullclines, like in this region, this region, this region, and this region, the vector field and solutions will travel in a consistent direction. And you can already see the directions here and here. Solutions in this region here, between this nullcline here and this one here, have to be going to the southwest. dx dt and dy dt are both negative because these straight line solutions are going to the southwest as well. And over here, they got to be going to the northeast because these are going to the northeast. That includes initial conditions down here as well for this side. The solution has to be going to the southwest here. dx dt and dy dt are negative. Then you're going to cross this y nullcline with a horizontal tangent. And then in this region, evidently, you're going to be going to the evidently you're going to be going to the northwest. dx dt is negative and dy dt is positive. You could confirm that by, for example, plugging in a point on the negative y-axis into dx dt and dy dt, into the vector field effectively. For example, if I could choose x to be 0 and y to be negative 1. If x is 0 and y is negative 1, and I multiply here, I get 0 minus 1 is negative 1. dx dt is negative. It's leftward motion. For dy dt, plug in x is 0 and y is 1. I get 0, y is negative 1. Negative 2 times negative 1 is positive 2. dy dt is positive. It's upward motion as well. And you're going to be forced to head toward the origin here. Now, are you going to go this way to head toward the origin? Well, you are going to have to cross the x nullcline. You need some extra knowledge to feel confident about that. The extra knowledge is, and this is going to come up in another problem, that most solutions will approach the origin along the straight line solution corresponding to the eigenvector for the eigenvalue that's closer to 0. Say that again. Most solutions will approach the origin tangentially along the direction of the eigenvector corresponding to the eigenvalue that's closer to 0 in this situation. The eigenvalue closer to 0 is negative 3, right? That's closer to 0 than negative 5 is. So most solutions are going to approach the origin tangent to this vector, tangent to this line, and you can see it seems like that's got to be the case here. So we're going to cross this nullcline vertically and head toward the origin there. Other solutions down here will more clearly cross. You'll have some symmetry involved. There's solutions starting up here. We'll do something symmetric. Draw in your arrows. Solutions that start here, for example, will go to the southwest, and they will cross these nullclines. Okay, they will go underneath the x-axis here and cross the nullclines because they again have to approach along this line tangentially in the end. It gets kind of hard to draw, but that is what's going to happen. What about initial conditions up here or down there? You still have to approach this line tangentially, so you're going to get this kind of behavior here and here. The only solutions that don't approach the origin tangent to that line, y equals 3x, is the solutions along the other straight line solution right here and right there. Okay, all the other ones do have to approach tangentially. So this is a pretty decent picture. It's a pretty tough skill to draw this thing. You really need to work on it with a lot of examples, so I'm suggesting you do that, and my students, you should do that. You probably don't have to draw as many solutions as I did, but the basic idea is good. All right, on to a problem evidently about complex eigenvalues. Yeah, show work to confirm that the eigenvalues of this matrix are complex numbers, 3 plus or minus I. For the particular complex eigenvalue, 3 plus I, the other eigenvalue is a complex conjugate of it, find the corresponding complex eigenvector. Then use something called Euler's formula to ultimately find a general solution and identify whether the equilibrium point at the origin is a spiral sink or a spiral source. Actually, we can do part D right away. The eigenvalues are complex with positive real part. That's going to mean the origin is going to be a spiral source. You're going to get exponential growth away from the origin. But it will be spiraling. Trig functions will become involved, cosines and the sines. And that's what happens with complex eigenvalues. Let's just go ahead and write down the characteristic polynomial using the trace and determinant. The trace here is negative 4 plus 10, that's 6. Determinant is negative 40 minus negative 50. Negative 40 plus 50 is 10. So the characteristic polynomial is lambda squared minus the trace times lambda, not plus trace times lambda, plus the determinant. Set that equal to 0 and solve for lambda. This is the word set here. Set that equal to 0. Solve for lambda. You're going to need the quadratic formula here. Lambda equals positive 6 plus or minus square root of 36, be 6 squared, minus 4 times 1 times 10 is minus 40 over 2 times 1. So yeah, that's 3 plus or minus square root of negative 4 over 2. Square root of negative 4 is the same as 2i. The 2's cancel, so I get 3 plus or minus I. Okay, so we've shown the work to confirm that. Part B, find the corresponding complex eigenvector. So once again, like in the other problem, we need to think about a minus lambda I times v equals 0, and we're looking for non-trivial solutions of this, non-zero solutions for v. And evidently, if it's complex eigenvalue, it's going to be complex solutions, a complex eigenvector. This becomes, if lambda is 3 plus I, we can really just focus on the first line. These equations are going to be, if I assume they're redundant, they're going to have the same solution set. I can just focus on the first matrix, first row of this matrix, and just subtracting lambda from negative 4. Negative 4 minus, in parentheses, 3 plus I times x minus 5y will equal 0. This is the same as negative 7 minus I. And then, so I need to add 7 plus I times x to both sides, or add 5y to both sides. Yeah, 5y equals negative 7 minus I times x. I was thinking I got a different answer when I thought about this before. Checking my work here. Okay, I'm wondering if I made a mistake here, but I think maybe I made a mistake when I did it before, actually. So then y would be negative 7 minus I over 5 times x. And I could then take x to be a free variable and say set it equal to 5. And that would mean I could take my complex eigenvector to be 5 for the first component and negative 7 minus I for the second one. That would be a complex eigenvector. Feeling a little uncomfortable that I got a different answer before. I think I'm going to just double check this with Mathematica here. And I'm going to do it using a matrix multiplication instead of a built-in command, just to confirm that this is okay. I don't want to make a mistake for you guys. So the matrix here is negative 4 and negative 5, 10, 10. And the vector is 5, negative 7 minus I. I need a capital I in Mathematica. A times the vector in matrix form is that, and lambda is 3 plus I times the vector in matrix form. Is it the same thing, is what I'm wondering. Where's my cursor? I lost my cursor. There it is. Yeah, okay, so it looks good. All right, I guess I made a mistake when I initially did the problem. All right, so that's part B. We found the eigenvector. Now part C. Use Euler's formula, Euler's identity, to ultimately find a general solution. So you got to know some things here. A complex solution. This is related to, what was it, the third problem where we were talking about real and imaginary parts of solutions? A complex solution is e to the lambda t times v, where lambda is your complex eigenvalue and v is your complex eigenvector. What we need to do is separate that into real and imaginary parts and choose the real and imaginary parts to form our general solution. They will end up being linearly independent real vectors. So again, the complex eigenvalue is 3 plus I, so I have 3 plus I times t. And by the way, this does in fact equal e to the 3t times e to the it. And then that's where Euler's identity comes into play with, is that e to the it times the complex eigenvector 5, negative 7 minus I. Yeah, Euler's identity says e to the it is cos t plus I sine t. Okay, that's really useful here. I also want to multiply by e to the 3t. E to the it is cos t plus I sine t. but I'm also multiplying each term by e to the 3t, so I get this times that complex eigenvector. Now I want to take this complex scalar and multiply it times each component. Multiplying times the first component is easy. The second one's trickier. I need to FOIL, and I want to think about separating the real and imaginary parts right away, I think. First times first is going to be real. There's no I. E to the 3t cos t times -7 is -7 e to the 3t cos t. The other term that's going to give you no I is going to be last times last, because I squared is -1. You're going to get this times -I. I squared is -1, so I times -I is +1. Positive e to the 3t sine t. I'm just going to go ahead and write this as two vectors right away here. YRE and YIM. I could have written it as one here initially, but to save time, I'll write it as two. That's going to be YRE. Those come from first times first and last times last. Doesn't involve an I. The things that do involve the I are outside times outside and inside times inside. Outside times outside is going to give negative. I already have the I here, so I get negative e to the 3t cos t. And inside times inside is going to give -7 e to the 3t sine t. And I already factored the I out, so I don't need an I inside there. With multiplying by the 5, the real part with no I comes from just this times 5, so you get 5 e to the 3t cos t. And for the imaginary part, factoring out the I get 5 e to the 3t sine t. And this is going to be my YRE of t, the real part, and this one's going to be my YIM of t, the imaginary part. And to save time, I'll just write the final answer here for the general solution as a linear combination like this, and I won't bother plugging those things in there. And notice there's no I here. Both YRE and YIM are real vectors. The YIM is just next to the I. I want my general solution for this real system up here corresponding to this real matrix A, this system here corresponding to that matrix A with no complex numbers in its entries, to be a real vector. So I don't want any I's down here. I'm just using I to get to the answer. And these are two linearly independent solutions. A general solution will be an arbitrary linear combination of them. Okay? They will span the solution space. The solution space will be two-dimensional. That's some information about vector spaces. And yes, like I said before, the origin here is a spiral source. And it's because the real part of the eigenvectors is positive, the 3 up there. That's going to correspond to the e to the positive 3t's coming in these spots. So solutions go away from the origin as t increases. If the real part had been -3, say, I would have gotten e to the -3t's here. It would be a spiral sink. The cosines and the sines are bringing in the oscillations, making spiraling. The phase plane is going to be spiraling toward the origin. Is it going to be counterclockwise or spiraling away, excuse me. Counterclockwise or clockwise, actually the best way to tell is to think about how this matrix maps the vector 1, 0 to think about the vector field at the point 1, 0. And it maps 1, 0 to a vector -4, 10. -4 in the x direction, 10 in the vertical direction. Yeah, it's going to be counterclockwise rotation here is the way it's going to be, and you could double check that. Okay, it's not a very careful drawing because I didn't make nullclines, but that's the general behavior. Spiral source. A couple more pages. This one right here takes a little while, but the very last page is all true-false multiple choice and goes pretty quick. Okay, I think I can do this one pretty quick as well. This is our Euler's method problem in 2 dimensions. Written in the system in scalar form and vector form. You can think of it either way. this is nonlinear and it's also non-autonomous, we can still use Euler's method. And I tell my students, with delta t equal to 0.5, approximate the solution at time 1, show your work. You can use either the vector form or the scalar form, and yeah, my students, you can do that, but I like using the vector form. I'm just going to go ahead and use the vector form. I think conceptually speaking, it helps you understand Euler's method better, so I just like using it. So first step is to say what y0 is. Y0 is the initial condition, y of 0. And that's 1, 2. Second step is to find what's called y1. What is y1? What is the next step thing that you get from Euler's method? You take the previous thing, the previous vector in the vector form, and add a change in the vector. And the change is found by taking the vector field, which represents the velocity vectors of solutions, write it as a vector field, f of t0 comma y0, the initial time and the initial point, times delta t. So that's going to be 1, 2 plus f of, careful, 0 comma 1, 2 times 0.5. That's the initial time. There's your initial vector. I need to plug t equals 0 into the vector field, as well as x equals 1 and y equals 2. There's the vector field. Plug in t equals 0, 0 plus, plug in x equals 1, 1 squared. I'm looking right there. For the first component, 2 times 0 is 0, plus y is 2 here. There's the y, times 0.5. So I get the vector 1, 2 times 0.5. That becomes the vector 0.5, 1. And that gets added to 1, 2. And the final answer here is 1.53, looks like, if I have not made a mistake. For y1, your approximation to the solution curve at time 0.5. Delta t is 0.5. I need to do one more step to get to time 1. So I'm after, ultimately, y2. That's y1 plus the change in the vector. Take the vector field, which again represents velocity vectors, evaluated at time t1, which is 0.5, and y1 times delta t. y1, if I have not made a mistake, hopefully I didn't make a mistake here. I think it's all good. Just double checking things. Yeah, I think it's good. 1.53 plus f of 0.5 comma 1.53, just plugging things in here. It's a little confusing if you're not used to dealing with vectors, but that's what I'm doing here. What happens when I plug into the vector field? Again, t is 0.5 now, x is 1.5. So I get, in the first component here, 0.5 plus 1.5 squared. Second component, I get 2 times t is 2 times 0.5 is 1, plus y is 3. 1.53 plus 1.5 squared is going to be 2.25, plus 0.5 is 2.75. This is 4. Looks like the final answer, if I have not made a mistake, is 4.257. Y of 2, y sub 2 is 4.257. That's an approximation to the true solution at time 1, not time 2, because the time step is 0.5. Hopefully I did not make a mistake there, okay? If there's a mistake, I'll make a note on the video. This one looks really long and really hard. It's actually way easier than it looks, okay? Now, I've taught my students about matrix exponentials. Maybe you've learned about matrix exponentials, maybe you haven't. I've also talked about flows. They're hard concepts, but if we use technology and we get the main points, this is actually an easy problem, okay? I've got a matrix A. I did make it lower triangular. That does happen to make the matrix exponential e to the ta power easier to compute. What is e to the matrix power of t times a? It's another matrix. Technically, it's defined, I think this comes up in a true-false question on the next page, as a Taylor series that is the analogous Taylor series for e to the x in terms of matrices. It's the analog of the number 1, which is the matrix I, the identity matrix, plus x, which is t times a. That's like acting like e to the x, where x is t times a. Plus, how does Taylor series for e to the x go? The next term is x squared over 2 factorial. We can write this as 1 over 2 factorial. T squared, a squared is x squared. Next term in Taylor series for e to the x is x cubed over 3 factorial, so we can write 1 over 3 factorial t cubed, a cubed, etc. It turns out it equals this, okay? And for my students, we end up relying on technology just to compute this thing for us. There are methods to compute them, and in fact, we'll get to that in exam 4, related to methods for what's called diagonalization, to compute e to the ta in many special cases without actually doing the infinite series. The matrix exponential is related to solutions. Okay, keep that in mind here. I'll explain it as we go here. Imagine we've got an arbitrary initial condition. Y sub 0 equals little x 0, little y 0. Okay, a generic initial condition. Part A says, write a simplified formula for the flow of the linear system. Your formula should be of the form of a vector with components that depend on t, x0, and y0. So we need to find those things. Okay? You just need to know a fact here. My students, you just need to know what's going on here, what I've taught you about what the answer will be. For A, I've said that the flow, the time t flow map for an arbitrary initial condition is the same formula as the solution, the unique solution for that initial condition at time t. And I've said that for a linear system like this, that linear system right there, I've said that is the matrix exponential, e to the ta, times the initial condition vector, y0. I call this the beautiful generalization. If you watch my lectures on differential equations and linear algebra, long about, lecture 20, 21, 22, somewhere in there, I call this the beautiful generalization. It generalizes what goes on in the scalar case, where you have an initial condition times e to the ta for a linear equation. If you imagine a being a number and y being a number, a function of t though, this is a number times e to the a times t. It's what you would get for a scalar linear equation, and so it generalizes to higher dimensions. What's this notation again? This is notation just for the solution curve, thinking of y0 as fixed and t as a variable. Use this formula. It gives you a parametric curve. If it's in a planar system like this, actually the eigenvalues would be 2 and -3. It's going to be a saddle point at the origin. This is going to be some curve going through the plane. Depending on the initial condition that you pick will determine where it is. But if you draw the phase portrait, it'll look like a saddle point at the origin. This time t flow map is the same formula, but you're just thinking of it differently. You're thinking of t as fixed and y0, the initial condition, as the variable. Kind of a strange thing to do. But when you do so, this becomes a linear transformation. E to the ta is a fixed matrix times this arbitrary variable vector. You think of y0 as a variable in that case, and it becomes a linear transformation. And it's a nice way to tie together differential equations and difference equations, differential equations and linear algebra, which I am still going to do in this problem, actually. Okay? All right. So that is, well, that's the vector form of the answer. As far as finding a simplified formula, I need to go ahead and use the formula for e to the ta. Just plug in that matrix and plug in this vector and go ahead and do the multiplication. Your final answer is going to be a vector. Got to multiply here. E to the 2t times x0 plus 0 times y0 is going to be e to the 2t times x0 for the first component. Second component is going to be more complicated. Second row dot product with this will be this times x0 plus this times y0. So you'll get -1/5 e to the -3t plus 1/5 e to the 2t times x0, and then plus e to the negative 3t times y0. And that's simplified enough. I mean, you could certainly use the distributive property and multiply this out, but that's okay to leave it like this. You also could group the e to the negative 3t terms together is another way to do it, but this is fine. And the first component, yeah, it's simpler. Just e to the 2t times x0. Okay, there's your simplified formula for part A. It's just this matrix times that vector. That's all it is. Okay, it looks really crazy complicated, but if you understand the concepts, that's all you have to do. Part B is also easier than it seems. You use your answer from part A to find this thing where I've plugged in t equals 1. It's called the time 1 flow map. Value the one iteration of the time 1 flow map for the specific initial condition, negative 1, 1. I could have done an arbitrary initial condition, but I decided to pick a specific initial condition. So you just plug in t equals 1 and plug in x0 is negative 1 and y0 is positive 1, and you're done. That's all you have to do. B phi 1 of y0, where y0 is this particular vector, I'll go ahead and put it in there, is, again, okay, plug in t equals 1, x0 is negative 1. I suppose we should simplify this when we do it. So I get negative 1/5 e to the 0 is 1 plus positive 1/5. Hey, those cancel out though. That's nice. That wasn't guaranteed to happen, but it did happen. x0 is negative 1. And then y0 is positive 1. And here we get e to the 0 is 1 times negative 1. That's a 0 there. So it looks like it's negative 1, 1. And that doesn't make any sense. I did not expect that to happen. What did I do wrong? Oh, I'm plugging in not t equals 0. T equals 1. Sorry. T equals 1. I was thinking so much about plugging in t equals 0 because I've done that so much. Negative 1/5. Plug in t equals 1, I get e to the negative 3 plus 1/5 e to the positive 2 times x0, which is negative 1, plus e to the negative 3 times y0, which is 1. And for the first component, I get e squared times negative 1. Okay, yeah, we can simplify this a little bit. Combine the e to the negative 3 terms. I got a positive 1/5 from this one and a positive 1. Looks like positive 6/5 e to the negative 3, and then a minus 1/5 e to the positive 2. And then this one's just a minus e squared. Okay? I'm sure I made a note on the video about it. Part C also sounds hard, but is also pretty easy. How's your answer related to the solution of the initial value problem at time 1? And this is the relationship between solutions of a difference equation and solutions of the differential equation. We've essentially iterated the time 1 flow map, one iteration for a certain initial condition. And what I teach, again, along about lectures 20, 21, 22, 23, somewhere in there, is that these things are just going to be equal. This thing, which equals that, will equal the solution for that initial condition, negative 1, 1, at time 1. Okay, done. That's all you have to say. You just need to know that when you iterate the time 1 flow map, it matches the solutions of the differential equation at that moment in time. If I did a second iteration of the time 1 flow map, the point I would be at would match the solution at time 2. If I did a third iteration, it would match the solution at time 3. That's something my students should know as well. I didn't write the difference equation here, but I could write it. The difference equation that I'm really iterating is yn equals the time 1 flow map applied to yn minus 1. And based on using the matrix exponential, that would be the same as taking e to the t times a, which is 1 times a, which is e to the a, times yn minus 1. That's the difference equation that I'm iterating here when I'm talking about applying the time 1 flow map. They're equal. I mean, you could just write that they're equal. That's how they're related. They're equal. That works because the system is autonomous. It actually works even with nonlinear autonomous systems that they're equal. But the formulas can be either much more difficult or technically impossible to write down in a simple form. Part D is just a knowledge thing as well. Suppose you've got a subset of the plane that has area equal to 5. What is the area of its image under the time 1 flow map? The area of the image of S under the time 1 flow map. Okay, you just need to know some things here. The time 1 flow map is implemented by e to the a, and so you need to know that the area is going to be multiplied by the determinant of e to the a. That's just a fact to know. So the area of the image of S under the time 1 flow map is going to be the determinant of e to the a times the area of S. E to the a, the matrix exponential when t is 1, is the matrix that implements the time 1 flow map. And therefore, that tells you how it affects the areas. It's always the determinant times the area. Technically, in general, it's the absolute value of the determinant. But the determinant of e to the a, in this case, will be a positive quantity. Yeah. And here is e to the a. And if I plug in t equals 1, I can do that. And being lower triangular, its determinant is the product of the numbers on the main diagonal. E squared times e to the negative 3 when t is 1. E squared times e to the negative 3. And the area of S is 5. So that simplifies to e to the negative 1 times 5. Or if you prefer, 5 over e. Okay? It makes the area smaller. This is compressing areas, which is kind of interesting to think about, actually, because the eigenvalues of the original system, this is about 1.84. The eigenvalues of the original system are 2 and negative 3, 1 positive, 1 negative. It's a saddle point at the origin. So it's not obvious that it's going to contract areas, but the negative eigenvalue is further away from 0 than the positive one. So it sort of has a stronger effect on areas when you're thinking about mapping points under the flow. If you don't know about matrix exponentials and flow maps, I guess you learned something a little bit there, but maybe you skipped ahead. Last page, true, false, and multiple choice. We can go pretty quick, I think. Number 9, given a square matrix A, the linear system dy dt equals ay has the origin as the only equilibrium point if and only if the determinant is 0. That is definitely false. It's if and only if the determinant is non-zero. If I had non-zero, then it would be true. Okay? It's analogous to the fact that a linear transformation implemented by a matrix will have a non-trivial kernel if and only if the determinant is 0. It has just the trivial kernel if the determinant is 0 of its matrix, assuming it's a square matrix. Okay, hope I said that right. It's the origin is the only equilibrium point if and only if the determinant is non-zero. So if I wrote equals 0, that's a false. This one was related to the formula for the matrix exponential. Given a square matrix A and a real number t, the matrix exponential e to the ta is defined by the infinite Taylor series. Yes, that's what I told you. That's true. Okay, that's the definition of it. Number 11. Which of the following second-order differential equations models a mass on a spring with spring constant k and damping coefficient b? Y is displacement from equilibrium, t is time. Okay, maybe you've memorized this, but maybe you haven't. It comes from Newton's second law and Hooke's law and just basic assumptions about how friction works. Newton's second law is F equals ma, which is the same as m times the second derivative of y with respect to t twice. And the forces are Hooke's law and damping, friction. Hooke's law is that the force opposes the position with a constant related to the spring constant. It's negative k is the constant of proportionality. And then damping, friction, opposes the velocity. Minus b times the velocity, and the velocity is dy dt. So the differential equation is ultimately that these things are equal. And if you rearrange by adding ky to both sides and adding b dy dt to both sides, you'll get 0 on one side. The answer is C. Okay. Sometimes we also divide everything by m. It's another way to write it. 12 is related to another comment from a little while ago on the problem with the phase portrait that I drew. Got a linear system, x nullcline, 11x minus 20y equals 0. That comes from the first row of the matrix. Y nullcline is 9x minus 16y equals 0. That comes from the second row. Eigenvalues are both negative. Corresponding eigenvectors are these. The origin is going to be a sink, non-spiral sink. Which of the following equations represents the line that most solutions are tangent to as t goes to infinity? I already mentioned that in that other problem. It corresponds to the line parallel to the eigenvector, which corresponds to the eigenvalue closer to 0. The Blanchard-Devaney-Hall book gives an argument for why that's the case for a particular example. My students, you should study that. But I'm just telling you, you can memorize it. So lambda 2 is the one that's closer to 0. Negative 1 is closer to 0 than negative 4 is. So v2 is the vector you want to focus on. 5, 3 corresponds to a line through the origin with a slope of 3/5. Y equals 3/5 x. Choice B. Okay. The other stuff, the other answers are kind of distractions, like related to the nullclines, for example. These two are kind of distractions. This one's maybe another plausible one based on that eigenvector, but you want the one that corresponds to the eigenvalue closer to 0. Here we have an unforced harmonic oscillator equation. What kind of harmonic oscillator is it? Undamped, underdamped, critically damped, overdamped. It's definitely not undamped because you've got some damping. There's your B. There's your K. So undamped is definitely not the answer. To decide if it's underdamped, critically damped, or overdamped, it's based on the eigenvalues of the corresponding linear system, which can be found just by thinking about applying the quadratic formula to this equation if you converted it to an algebraic equation involving powers of the eigenvalues. That does turn out to be the characteristic polynomial. And the thing you need to look at is the discriminant, right? The thing under the square root, and whether it's positive, 0, or negative. That's going to determine whether you have real eigenvalues, a repeated real eigenvalue, or complex non-real eigenvalues. And that's going to be b squared minus 4mk. Just like in the quadratic formula, it's b squared minus 4ac. The a is m, the c is k. So that's 2 squared minus 4 times 1 times 2. 4 minus 8 is negative 4. Negative under the square root, you're going to have complex eigenvalues. There's going to be oscillation involved in the formula for solutions. Spiral sink at the origin. Not enough damping to prevent the spiraling. It's underdamped. There's not enough damping to prevent the spiraling. When you've got a lot of damping, that's overdamped. You have two distinct real eigenvalues that are both negative, and the origin's a non-spiral sink. There's so much damping that it prevents any oscillation, any spiraling. This is the last question. Which of the following is an approximate equation for the time 1 flow map of a scalar autonomous differential equation? It's the same principles as the other one, but easier because it's scalar. We need to solve the generic initial value problem and use that formula. That is effectively the answer. So this is something you can solve just by thinking about it here. Solution is y0 e to the 3t. Okay, that I could write as, say, little phi sub y0 of t. I used capital phi on the previous page. Usually you think of y0 as fixed and t as the variable, and this is a function of t that solves the differential equation. But I also can think of it as a time t flow map, and I use this other curvy phi, and think of t as fixed and y0 as the variable, and then it becomes a linear function of y0. And for the time 1 flow map, time 1, I plug in t equals 1. So curvy phi 1 of y0, plug in t is 1, I get e cubed times y0. And e cubed, yes, is about 20.0855. 20.0855. Yes, that's an approximate equation for the time 1 flow map here. So therefore, the answer is D. Okay? And that's the end of the video. Thanks for watching.